Oh, yeah.
All right, so today we're going to start in on our next category of reactions, which is the substitution of alcohols. All right, so we're going to swap out that hydroxyl group for some new set of atoms. Okay, so let's take our alcohol. All right, if we're going to swap it out with some nucleophile here, I'm just going to use Nu for like variable generic nucleophile. Nucleophiles are electron rich, so they at the very least have a lone pair and oftentimes have a negative charge as well. All right, and if we did our substitution reaction, all right, that means our nucleophile attacks and kicks off that hydroxyl group, leaving us now with our nucleophile bound. All right, but what would be our leaving group here? What happens to this chunk right here? All right, it's coming off of our molecule. So OH, I'm going to put in these lone pairs here. What else am I missing? Another lone pair, right? So first of all, that should make everybody's eyes hurt a little bit. Oxygen doesn't have a complete octet. So oxygen will never not have a complete octet. Importantly, this arrow right here represents that this pair of electrons has now become a lone pair on that oxygen. All right, this lone pair right here used to be that bond. Cool. And this thing right here, I'm missing one other thing, that lone pair and negative charge. Cool, and we have a special name for this thing. All the way back in general chemistry, we were introduced to this guy. What is this? Hydroxide ion, okay? Now, a hydroxide ion, the very first thing you would have learned is that it was a strong base, which also means it is a terrible leaving group. All right, so unless you have the strongest nucleophile in the frickin' world, you're not going to be able to kick off that hydroxide ion. It's just a terrible leaving group. You can't get it off. All right, so our substitution of alcohols here, we're always going to have the same strategy. All right, and that is to replace that hydroxyl group with a better leaving group. All right, so this substitution of alcohols business is a little bit of a scam because the first step is to make it not an alcohol anymore, and then we can actually do our substitution reaction. All right, we're going to have two methods that we're going to see. Number one is to convert to what's called an alkyl halide. All right, where we're going to replace that OH with a halogen of sorts, either chlorine, bromine, or iodine. All right, or we got this kind of fancy new reagent that we can use, which is called tosyl chloride. All right, and this will convert that OH to an OTS. And we'll talk more about what this is here in a second. But the bottom line is that this is just a fantastic leaving group. All right, so we have this special reagent that we can use whose whole goal in life is to convert a hydroxyl group into a good leaving group. All right. Our first method kind of goes back to our organic chemistry 1 here. One of the first set of reactions that you would have learned about, actually towards the end of the semester, would have been starting with alkyl halides. Alkyl halides, those halogens are great leaving groups, so we can convert an alcohol into a halogen, into an alkyl halide, in order to do our substitution reaction. Okay? So we're going to start there. We're going to convert alcohols into alkyl halides. Okay? All right, and the first thing that we're going to do is we're actually going to break the world of alcohols up based on their classifications. We're first going to talk about primary and secondary alcohols. All right. The reason that we're going to break the world of alcohols up, we're going to talk about primary and secondary, and then we'll talk about tertiary towards the end of class, is because these react with different mechanisms. Primary and secondary alcohols will undergo what are called SN2 substitution mechanisms. All right, we're going to see these a few, so let's just do a generic mechanism here for SN2. That means that we have a molecule that has some good leaving group. All right, I'm actually going to, and we'll see why this in a second. I'm going to put it in the middle. All right. It gets attacked by some nucleophile. Okay? And in an SN2 mechanism, the nucleophile attacks and the leaving group leaves all in one step, all in one shot. All right? So importantly, the nucleophile has to attack from the opposite side of where that leaving group is. Now I have my nucleophile attached and my leaving group is off in space. All right, so in our SN2 mechanism, we have what we call this backside attack. Okay. Cool. So this is going to be important to keep in mind for our for our primary and secondary alcohols, is they're undergoing this substitution mechanism. All right. This also has implications on the stereochemistry. So if instead I were to make this a very stereospecific molecule here with this dashed bond or with this wedged bond in an SN2 mechanism, since the nucleophile attacks from the opposite side, we get this inversion in our stereochemistry. Our leaving group would be on a wedged bond, which means that my new nucleophile bond would be a dashed bond. All right? And likewise, if it was flipped, if I started out with a wedged bond, it would become a dashed bond, right? We always see this stereochemistry inversion with these SN2 mechanisms. That's a result of that backside attack. So we just want to make note here that we have a stereochem inversion. All right, so again, we're making alkyl halides here. So let's start with a primary alcohol. All right, so just something as simple as 1-propanol. All right, we kind of got these fancy reagents that we use, and we're not going to look at our mechanism. Thionyl chloride and phosphorus tribromide. All right, but suffice it to say that they both work through an SN2 mechanism and by making that primary alcohol first into a better leaving group before replacing it with a halogen. So thionyl chloride will create an alkyl chloride, and phosphorus tribromide will create an alkyl bromide. All right, and remember the whole shtick here is now these are great leaving groups, and we can go and treat them with some nucleophile and get a substitution reaction. That's what we're building up to, right? But the first step was to make them into good leaving groups. Okay? If we want to do a secondary alcohol, and we're going to look at a stereospecific secondary alcohol. All right, again, since these are going through these SN2 mechanisms, everybody take a second and draw me my product here. What would we expect? Importantly, since this is an SN2 mechanism, we would see an inversion in our stereochemistry. So now that wedged bond of my alcohol will become a dashed bond in my products. Okay, let's just make note, I didn't have to worry about that with primary alcohols. I just went ahead and drew these all with these straight line bonds. Why is that? Well, because this primary carbon by definition has 2 hydrogens on it, 2 identical groups, so it's not a stereocenter. So great, I have this inversion of stereochemistry that occurs, rather not a stereocenter. Right? Or great, I have this SN2 mechanism. I do see an inversion about that carbon. It just doesn't have any sort of a consequence in terms of the stereochemistry because there are 2 hydrogens on there. That's not a stereocenter. Okay? If it's a secondary alcohol, all of a sudden I would have to worry about that. Cool. All right, so as we saw in our substitution, we need some nucleophile here. All right, so let's just take a second and take a step back and just talk about what the heck it means to be a nucleophile. All right, so I got that one question that I always ask you. Which one is the nucleophile? The electron-rich one or the electron-poor one? Electron rich, right? Our nucleophiles are electron rich. All right, and we're going to bunch up the world of nucleophiles into 2 buckets here. We have our strong nucleophiles. All right, and we're going to group these by that nucleophilic center, which which atom is actually holding on to all of that negative charge, all of that electron density, all right? So our oxygen strong nucleophiles, they're all going to have this generic formula, some number of carbons and or hydrogens plus that oxygen with a negative charge. All right, so this could be a hydroxide ion, something as simple as a hydroxide ion, or that R could represent 10 carbons or something like that, right? All right, as long as it has that oxygen with that negative charge, 3 lone pairs and a negative charge. Okay, we can also talk about nitrogen nucleophiles. Okay, those could have 2 alkyl groups, but that nitrogen has 2 lone pairs and a negative charge. All right, and again, what common feature do these nucleophilic centers have? That negative charge, right? A bunch of electron density. What's the key telltale sign of a bunch of electron density? A negative charge. Okay, I will just note, oxygen nucleophiles you'll see all the time. I have never once in the wild seen a nitrogen nucleophile, a deprotonated nitrogen. They're just super dangerous to work with, super strong bases. So anyway, in our pencil and paper chemistry, we can do it all we want. Practically speaking, you probably won't ever run into one of those guys. All right, we can also have a carbon nucleophile, strong nucleophile. But carbon's even more furious about being deprotonated than nitrogen is. So there's really some only special cases that you see. Not any old carbon will have a negative charge on it. They're sort of stabilized by these triple bonds. So a good example of one that you do see is a cyanide ion, where that carbon has that lone pair and that negative charge. That's a nucleophilic carbon. All right, you would have learned in your alkyne chapter that if you had a terminal alkyne, you can also deprotonate it with a strong base. All right, and then there's another one that we're going to lump into this category too that's kind of brand new, and that is our Grignard reagents. Remember, our Grignards have that nucleophilic carbon, a carbon with a ton of electron density. I guess I'm just going to do R. All right. And then lastly, another atom that is just a particularly good nucleophile is sulfur. Sulfur lives in the same column as oxygen on the periodic table, so it's got the same bonding patterns, right? If it has 1 bond and 3 lone pairs, it'll have a negative charge. All right, what makes sulfur kind of special in this category is that we can even have a neutral, what's called thiol. We'll talk about those next week. But even if it doesn't have a net negative charge, it is still classified as a strong nucleophile, right? That sulfur, even though it's neutral, sulfur is just really big and has these electrons that can make their way to that electrophilic center easy. They are good, strong nucleophiles, even if they're neutral. All right, so this is our first bucket of nucleophiles, our strong nucleophiles. We also can have weak nucleophiles. All right, these are things that really don't play the role of a nucleophile unless there's just a really good electrophile lying around. Again, we'll break those into our nucleophilic center. Oxygen. All right, this would be water or some sort of an alcohol, or nitrogen. All right, this would be ammonia or some amine. Okay? And structurally, what do we notice is the big difference between our strong and our weak nucleophiles? The negative charge, right? So the vast majority of our strong nucleophiles have negative charges. There are two oddballs, that neutral thiol, as well as our Grignard, which we talked about. That's kind of a weird one, but there's that metal in there, so it's already kind of in a weird category all by itself. But yes, generally speaking, our strong nucleophiles have these net negative charges. Our weak nucleophiles, they all have lone pairs that they can donate. They're still electron rich, but they're neutral, right? So they're not quite as much electron density. Okay, cool. So the whole point of this was the substitution of alcohols, right? So we're going to take an alcohol. We want to substitute out that hydroxyl group. So we're going to first convert it into a good leaving group, using one of those two methods, either the thionyl chloride or the phosphorus tribromide. And then we're going to treat it with some nucleophile, all right? All right, so everybody take a second, see if you can't tell me what the product would be of this reaction. Right, so after that first reaction, I have converted that alcohol into a good leaving group, my alkyl chloride. All right, we don't know the mechanism for this one. It actually is in your textbook if you're curious. Suffice it to say that the thionyl chloride attaches itself to the oxygen, making it a better leaving group before that chlorine goes on there. But regardless, we're going to sort of gloss over that mechanism, other than to say it's SN2. For this one, though, we can definitely draw our mechanism. That lone pair on that alkoxide is going to come attack that carbon and kick off that leaving group. Just a classic SN2 mechanism. All right, and so what we'd be left with is now, let me color our oxygen that got attacked here in blue. On the other side is now a new bond with what element? Oxygen, right? That was my nucleophile. Cool, and we can just note this carbon here would be what? If the oxygen's my nucleophile. Electrophile, yes. Nucleophiles attack electrophiles, right? And so why is that carbon left relatively electron deficient? Well, because it's in this polar bond with this more electronegative chlorine atom. Right? Not only that, but because chlorine's such a good leaving group, it makes that carbon even more capable of accepting that pair of electrons. Okay? Cool. So we had to do two steps here, but we did our substitution of our alcohol. All right? One more thing to note, I should have noted up here, our strong nucleophiles, why did we put these into these buckets here? Because these will react with our alkyl halides. Weak nucleophiles will not. All right, at least now without a little bit more of a caveat here. Okay, all right, so now let's do another one. But now we're going to use our stereospecific alcohol. Just for fun, we're going to instead use that phosphorus tribromide in our first step. And then we'll do that cyanide ion. Right, so importantly, that first step is an SN2 mechanism. So we see this inversion in our stereochemistry. Oops. Now we got that good leaving group on there, all right? Our second step, importantly, is also an SN2 mechanism. Which one of these is my nucleophilic center? They both have lone pairs, nitrogen or carbon? Carbon, right? First of all, we put it in the carbon category. Second of all, carbon is the one that has that formal charge of -1. All right, so it's going to go attack that back side and kick off that bromine. So now, yeah, I flipped my stereochemistry in that first step, but now I've flipped it back again, right? Now I'm back at my dashed bond, okay? And I'm going to be good here because this is a carbon-nitrogen triple bond. I'm going to draw it in this linear fashion here. Carbon you could actually leave implied as well, just kind of crash that triple bond right there. It looks a little weird, so I'm going to keep that carbon there. Notice because your nucleophile has a carbon atom on it, you actually increase your number of carbons in your product by 1, right? That nucleophile added an additional carbon to our molecule here, okay? But this is our substitution of our alcohols, first by creating these alkyl halides, and then by treating them with one of our strong nucleophiles. All right. We had another method we said, and this is using what's called tosyl chloride. Okay, so first of all, what is tosyl chloride? We got a benzene ring with a methyl group on one side and something that looks a lot like a sulfonic acid group. All right, but instead of having 3 oxygens, it has 2 and a chlorine. Okay, you will see this abbreviated just TSCl. So remember we said that if we just took a generic alcohol and we treated it with a nucleophile, that hydroxyl group is a terrible leaving group, so no reaction will occur. All right. If instead we first treated that alcohol with that tosyl chloride, what it does is now that oxygen from my alcohol is going to still be there. But now it's got that big old tosyl chloride molecule on it, right? Actually without the chloride, just the tosyl part. So now it's got a sulfur double bonded to two oxygens. All right, so that tosyl chloride molecule attaches itself to that alcohol group. All right, we don't really bother drawing it out all the time. We instead say OTS, right? Where the TS represents that part of my molecule there. Okay? All right, and the whole shtick here is that this thing, this tosyl group that's on there, is an amazing leaving group. Which means that when you treat this with your nucleophile, you will get your substitution reaction. Right? So again, in both of these, our topic of discussion today, substitution of alcohols, the first step has to be to convert that hydroxyl group into a good leaving group. All right, first we were talking about turning it into a halogen. Now we're talking about this new special molecule here, this tosyl chloride, whose whole job in life is to convert a hydroxyl group into a good leaving group. All right, so it attaches itself on there. Now that thing can leave very easily. I guess actually I got to include my oxygen. That's also leaving. Okay. Last thing is just the stereochemical considerations of this tosyl chloride. So let's take our alcohol. We're going to use a stereospecific alcohol. Okay, if the first thing we do is treat it with tosyl chloride, importantly, it didn't do any substitution, right? That oxygen from my alcohol was still on there. All it did was replace the hydrogen. So this is not an SN2 mechanism here, which means when that tosyl chloride attaches itself, I will still have that same chemistry that stereochemistry that I started out with, right? My wedge stayed a wedge. There was no stereochemical inversion because it wasn't an SN2 reaction. All right, but now we're going to go one more step and we're going to treat it with our nucleophile. Now this is an SN2. My nucleophile has to attack from that opposite side of my leaving group. So now I will get a stereochemical inversion. All right. Cool. So now just to have these stacked on top of each other, so we're super clear here. What are the differences? between our conversion method 1 and 2? Right? Between my alkyl halide conversion and my tosyl chloride conversion. All right, so let's take our stereospecific alcohol. All right, we're going to create two pathways here. One using method 1, where we first convert to an alkyl halide. Oh my gosh, driving me nuts. All right, we'll use our thianyl chloride, and then we'll use that strong sulfur nucleophile. And in our second pathway, we're going to instead use our second method. We're going to use that tosyl chloride. And then we're going to use that same sulfur nucleophile. All right, given our past two examples, everybody take a second and see if you can't give me the products here. What is the difference between these two methods? So, what's the big difference here? All right, importantly, there really wouldn't be a difference if there wasn't this stereocenter here. So if we were talking about a primary alcohol, for example, all right, but the big difference here is that if I use my thianyl chloride first, the SOCl2, I would get a stereochemical inversion. And then when I did my SN2 substitution here, I would flip it back to that wedged bond. Right, so we get two inversions in our stereochemistry, taking us back to what we started with. If I use the tosyl chloride instead, importantly, this does not change the stereochemistry of that alcohol. So that TS group is just going to attach onto that alcohol, still on that wedged bond. But then when I get my SN2 mechanism here, I will get that stereochemical inversion to that dashed bond. All right, so our big difference here is in our first method, both the conversion to a better leaving group and the subsequent nucleophilic attack are SN2 reactions. So we have our stereochemistry flip in the first step and then flip back in that second step. And if we use our tosyl chloride, this one is not an SN2 first step here, so our wedge bond stays wedged. And then when we do our SN2, then we get our stereochemical inversion. Okay? So, again, if we used a primary alcohol, we'd get the same product regardless of which path we took. But if we use this stereo-specific secondary alcohol, then it is going to depend. All right? So now we talked about primary alcohols and secondary alcohols in one bucket. Now we're going to talk about tertiary alcohols. All right, and our big difference with tertiary molecules that have good leaving groups is that they instead undergo what are called SN1 mechanisms. Right? So if we have a reaction mixture with this tertiary molecule with its good leaving group, the first step is that leaving group falls off, leaving us with a carbocation intermediate. In a second step, the nucleophile attacks that carbocation, and that's how I get my substitution product. All right, because these go through these carbocation intermediates, all right, first of all, what do we sort of always note about our carbocation intermediates? We gotta watch out for shifts. In this case, we're gonna get lucky though, because that carbocation is already on the most substituted carbon that it could be, right? It's a tertiary carbon, okay? So that we don't have to worry about here. What we do have to worry about though, or rather consider, and actually it's kind of best case scenario, is this will erase, or rather we will get a racemic mixture meaning all possible stereoisomers. And so why is this a good news? This means we don't have to worry about dashes and wedges. When we do racemic mixtures, we can just do our straight line bonds, right? We can represent our stereocenters as, I don't know, it's both of them in there, right? That's what a racemic mixture is, a mixture of equal parts dash and wedge bonds, which again, we can represent with our straight line bonds. Right? Because these SN1 mechanisms have these carbocation intermediates. Carbocation intermediates are just about the best electrophiles that you could possibly have, which means that we get to use our weak nucleophiles. Okay, we can use this with our carbocation electrophiles. They are such good electrophiles that your nucleophile doesn't have to be all that great. All right, so our strong nucleophiles, we're going to reserve those for primary and secondary alkyl halides, as well as primary and secondary tosyl groups, tosyl molecules. All right, our weak nucleophiles are going to be reserved for those carbocation intermediates. right, so we still have to convert to a good leaving group. Right, we still need that good leaving group before any SN1 substitution can occur. All right, we can again convert to an alkyl halide. But this alkyl halide formation here, we don't want to use our thionyl chloride or our phosphorus tribromide. Those are sort of specific to those SN2 mechanisms. And besides, they're way more expensive than what you could actually use that's just super efficient. And that is just a strong acid like HCl or HBr. Both of these would be just fine. Way, way cheaper, and we'll convert to that alkyl halide just as efficiently. Or we can still use our second method, that tosyl chloride. And that will convert in the exact same way that we saw before. That tosyl group will attach to that oxygen. All right. And again, the whole reason we would do this is because now we have these good leaving groups. All right, so then these would all be ready to undergo this SN1 mechanism with some nucleophile. All right, and we'll pick up with that next time. We'll do some specific examples with our tertiary alcohols.